Hi students, I am Randeep Singh and today I would like to teach you inertia and Newton's laws of motion. First of all, we will talk about inertia. Inertia of a body is the inability of the body to change its state on its own. The state of the body may be either state of rest or state of motion. For example, a pen at rest will always remain at rest unless I apply an external force to move the pen. Similarly, a book at rest will always remain at rest unless we apply the external force. So simply inertia is the inability of the body to change its state of rest or of uniform motion along a straight line. Now the inertia is related with the mass of the body. For example, if we have a box which is empty and we can easily move that box by applying some sort of force. Now if we fill the same box with some stones and books and other materials, we need to apply the extra force to move the box in that direction. This is due to the increased mass of the box. Its inertia has also increased, and due to the increased inertia of rest, it don't want to change its state of rest. So mass of a body is directly related with the inertia of the body. So in that case, we need to apply the extra force to move the box in that direction because the mass has increased. Now another example, we can easily move the ball by applying some force because it has a less inertia of rest as compared to a stone which has a very high mass as compared to the ball, and we practically cannot move a very large stone or rock by applying some force because it has a large inertia of rest. Now there are three types of inertia: inertia of rest, inertia of motion, and inertia of direction. The basic concept in all these three types is same. Now we will study inertia of rest. Inertia of rest means simply a body at rest will remain at rest unless we apply some external force. Now the example of inertia of rest. For example, you have noticed that when you are sitting in a bus or train and the bus or train starts suddenly, you feel a jerk in the backward direction. This is due to the fact that lower part of your body starts moving with the bus or train, but the upper part of your body tries to remain at rest due to inertia of rest. Inertia of motion, it simply means that if a body in motion will always remain in motion unless we apply some external force to stop the motion of the body. So simply a body cannot change its state of motion on its own. The same example, for example, when you are sitting in a bus and bus is moving with some velocity, and if a bus suddenly stops, your body may feel a jerk in the forward direction. This is due to the fact that lower part of your body comes to rest with the bus, but the upper part of your body tends to continue in the motion due to inertia of motion. Now the next type is inertia of direction. Means that a body cannot change its direction of motion on its own. We need some external force to change the direction of the motion. For example, you are sitting in a bus and bus is moving with some velocity in the forward direction, and after some time bus takes a U-turn. Then your body may feel a jerk in the outward direction. This is due to the fact that your body tries to remain in the original direction of motion, but the bus has changed its direction of motion. That's why your body may feel a jerk in the outward direction. Now we will study Newton's laws of motion. Newton's first law of motion. It states that a body continues to be in a state of rest or in a state of uniform motion along a straight line unless some external force is applied on the body to change that state. Newton's first law of motion is also called law of inertia. There are few examples of Newton's first law of motion. For example, a ball or a book at rest will always remain at rest unless we apply some external force to change the state of rest. For example, a pen at rest will always remain at rest until we apply some force to change the state of rest. Similarly, if a ball is moving with certain velocity in that direction and we want to stop the motion, then we have to apply a force in the opposite direction to stop the motion of the ball. Now there is an interesting situation. Some students say that a ball comes to rest on its own after moving to certain distance. Actually, the thing is that when a ball moves on floor or any other surface, the ball is under the action of dissipating forces, that is force of friction and air resistance. And due to that force of friction and air resistance, ball comes to rest after moving to a certain distance. And if we will be able to remove these dissipative forces, then ball cannot come to rest on its own. Now the ball is moving with certain velocity in the forward direction, and we want to change the direction of motion of the ball at point here. Then we need to apply some external force on the ball to change the direction of motion, because it cannot change its direction of motion on its own. So that's all about Newton's first law of motion. Now moving further, Newton's second law of motion. It states that the rate of change of linear momentum of a body is directly proportional to the external force applied on the body, and this change takes place always in the direction of the applied force. That means force is directly proportional to change in linear momentum upon time taken, and it is denoted by dp by dt, because linear momentum is denoted by p, and force is a vector quantity because linear momentum is a vector quantity. Now suppose a body of mass small m and its initial linear momentum will be equal to mass into velocity, that is m into u. U is here initial velocity, and its final linear momentum will be equal to p2. P2 is equal to mass into velocity, that is m into v, and the change in linear momentum comes out to be p2 minus p1. Putting the values, it will become m into v minus u, and putting all these values in the formula, f will be proportional to m into v minus u upon t, or we can simply write dp by dt, and the quantity v minus u by t will be acceleration, because v minus u is the change in velocity, and change in velocity per unit time is acceleration. That is, force is directly proportional to mass into acceleration, or we can simply put the value of momentum here. Value of p is mass into velocity, and mass is a constant of derivative, and dv by dt is acceleration. That means it comes out to be mass into acceleration. To remove the proportionality, we have put a constant here, that is k, and if f is equal to 1 and m is equal to 1 and a is equal to 1, the value of k will be 1, and simply force is equal to mass into acceleration, and again force is a vector quantity and acceleration is also a vector quantity, and or acceleration comes out to be force upon a mass. Now there is an interesting question, that whether the mass of a body always remain constant during the motion of the body. The answer is no. If the body is moving with a very large velocity comparable to the speed of light, that is 3 into 10 raised to power 8 meter per second, then the mass of the body changes with the motion of the body. But as we are studying classical mechanics or analytical mechanics, and in our day-to-day life we cannot attain that much amount of velocity that is comparable to the speed of light, so you can simply apply Newton's second law of motion in all the conditions. So there are a few examples of Newton's second law of motion. The first is catching a cricket ball. When a cricket player catches a ball, he moves his hands backwards, and by doing so, he is simply increasing the time during which the final velocity comes to 0. Or simply, if he increases the time of rate of change of momentum, then the force will decrease, or the player wouldn't get injured by doing so. And another example is use of seat belts in cars. Now, if a person is driving a car and the car is moving with a very large speed, and if the person suddenly applies the brakes, then the person may feel a jerk in the forward direction and may get injured. But if the person is wearing safety seat belts, then due to the stretchable property of these safety belts, the person has increased the time during which the change of momentum takes place, and simply decreases the acceleration, and hence less force will act on the body of the person, and hence person wouldn't get injured, and therefore all of us must wear safety belts while driving. Now moving further, Newton's third law of motion. It states that to every action there is equal and opposite reaction. And there are several examples of Newton's third law of motion. The first is of a weighing machine. Now here is a weighing machine and there is a body of mass small m lying on the weighing machine. So weight of the body, that is mg, will act downward on the weighing machine, and according to Newton's third law of motion, equal and opposite reaction, that is r is equal to mg, will act in the upward direction, and the weighing machine will simply reads the weight of the body, or simply reads the reaction of the weight of the body. Another example is of swimming. In swimming, a person applies a force on the water in the backward direction and experience a equal and opposite reaction in the forward direction. Another important example is flying of rockets. It is based on the principle of Newton's third law of motion and the law of conservation of linear momentum. For example, during the motion of the rockets, fuels such as hot gases burn with the greater thrust in the downward direction and experience equal and opposite reaction in the upward direction, hence fly in the upward direction. Now I have demonstrated only a few examples, but in our day-to-day life you can experience a lot of examples which are based on Newton's laws of motion, and try to make a list of all these. Now our last example is that if an apple under the action of gravitational force of earth falls on the ground, that is action mg acts on the downward direction on the earth, and equal and opposite reaction, that is r, will be equal to mg acts on the earth, but the earth doesn't move in the upward direction. This is due to the fact that force is same which is acting on the apple as well as on the earth, but the mass of earth is very large as compared to the mass of the apple, and practically acceleration produced on earth is 0. So thank God earth doesn't move in the upward direction. So that's all about Newton's laws of motion. I hope all of you understand well. Thank you. Stay safe and healthy.